Okay, let's do a sound check. Can everyone hear me on the other end?
Yep.
Yes.
Great. Okay, let's begin the class. First question I wanted to ask is, did everyone receive my email from yesterday? Yes? Okay. So let me just briefly say, so the midterm will happen on 2 days. So the first group, so the midterm is next week. And then on Wednesday, the Georgia group will take the midterm. Okay. And then on Friday, the Bulldogs will come in and take the midterm. Okay. And I think I gave sort of fairly detailed instructions about how things are going to work. Hopefully everything will go well for next week. So I will finish the material on inverses today. And then on Friday, I will start the review for the midterm. So the review for the midterm will be on Friday. So I'll discuss like the definitions you'll need to be accounted for on the midterm. I'll also talk about certain types of problems that you'll be expected to know how to solve. And so I'll sort of split the review into 2 parts. So it'll be Friday and Monday. Okay. And what I'll do is I'm not going to just review for the entire time. So after a certain point, I'll stop and then I'll leave it open for questions. So there'll be a Q&A session on both days. Okay. So I encourage you to think about problems or sort of concepts that you may want me to go over during the Q&A session. So if you have any questions, please write them down, and so we can actually discuss them on Friday or even Monday. Okay, any questions on this? Good. All right, so let's go back to inverses. And so what we'll do is we'll sort of start with our setup. So again, A is an n by n matrix. Okay. So A has an inverse. If and only if there exists a C, which is an n by n matrix, such that A times C is the identity and C times A is the identity also. Okay. Now, again, we saw that the inverse is unique if A is invertible, and so C we write out as A inverse. Okay, so this is the notation. All right, now last time we went over a formula for 2 by 2 inverses. And then what we did was we discussed how to find inverse for arbitrary m by n matrices. So define an inverse for A. So what we do is we start with A on this side, and we put the identity on the right-hand side. And then what we're going to do is we'll just perform Gaussian elimination to transform the right-hand side into A inverse, and then the left-hand side into the identity. Actually, I should say the other way around, but that's okay. So you apply Gaussian elimination, so you transform A into the identity, and out will pop the inverse on the right-hand side. Okay, so we actually did this for the 2 by 2 case in the last lecture. And so what I want to do today is I want to start off with a 3 by 3 matrix, something where it's not clear what the inverse is, and show you that this is a very effective way to do this. Okay, so let's do an example. So the problem is to find A inverse where A is the following matrix. 1, 4, -3, -2, -7, 6, and 1, 7, -2. So this is the matrix. It's a 3 by 3 matrix. All right, so we're going to sort of apply the procedure that I mentioned before. Stick A on one side and the identity matrix on the other. Okay, so we're going to leave enough room. So A is on one side. And then we put our little fence, and then we put the identity matrix on the other side. All right, everybody okay with that? All right, good. All right, so in doing so, we're really just performing Gaussian elimination like 3 times, but all at once. All right, so, okay, so this is good. And so, so we start off by thinking of 1 as the pivot here. We want to knock out the -2 and the 1. So the first step is to multiply the first row by 2. Add it to the second row and put it in the second row. So 1, 4, -3, 1, 0, 0. And what do we get? We get a 0 here. I get 8 plus -7, that's 1. I get -6 plus 6, that's going to be a 0. And then I get 2 plus 0, that's a 2. And then I get a 1, and I get a 0. Okay, any questions on this? All right. Let's continue on. So now I want to get rid of the 1 down at the bottom in the third row. So I'm going to multiply the first row by -1, add it to the third row, and then put the result in the third row. So I got a 0 here. I got -4 plus 7, that's a 3. And I got a 3 plus 2, that's going to be, all right? Let's see, 3 plus 2, I get 1. So let's make sure that's right. -3. Oh, there's a -2 there. Sorry about that. I copied this down wrong. Let's just make sure. 1, 4, -3, -2, -7, 6, 1, 7, -2. Okay, now it's right. So I get a 3 plus -2, which is a 1. Okay. And then what do we get? We get -1. And then we get a 0. And we get a 1. Okay, is everyone all right with that? And make sure you don't drop minus signs like what I did. not a good thing, because if you make a mistake at the beginning, it sort of exacerbates itself towards the end. Okay, good. All right, now the next thing is I want to get rid of the 3's, so I'm going to use that as a pivot. So let's multiply by -3 over here. And let me just get this in an upper triangular form. Let's do this. 1, 4, -3, 1, 0, 0, 0, 1, 0, 2, 1, 0, 0, 0, 1. Okay, -3 times 2 plus -1 is -7. The next one is -3. The last one is 1. All right. Any questions up until this point? Oh, we got this. Okay. Now, the nice thing is that we have a 0 sort of right above this 1. So what we have to do now is we have to use the 1 and sort of like stand on our heads and sort of, kind of reduce things in this column over here. And also we have to kill something over here too, all right? All right, so we're sort of using Gaussian elimination, but sort of standing on our heads. Okay, so now I'm going to multiply this row by 3. Okay, and then I'm going to add it to the first row and put it in the first row. Okay, so let's do that. 0, 0, 1, -7, 3, 1, 0, 1, 0, 2, 1, 0. Okay, now let's see what we get. So we get a 1 here. We get a 4. And we get a 0. Okay. And then we get -21 plus 1 is -20. Okay. And then what do we get? We get -3 minus, so it's -9. Right? And then we get a 3. Okay. So we only have one more step left to do, and that's to actually get the 4 out of the way. Right? So to get the 4 out of the way, we're going to use this to knock it out. So I'm going to multiply by -4 here, and then sort of knock the 4 out in the first row. So we're going to take second row times -4, add it to the first row, put it in the first row. So these stay the same. Okay. So what do we get? We get a 1 here. We get 0, and we get a 0. So that's good news. And then what do we get? We get -20 plus -8. It's -28. Interesting. Okay. And the next one we get is, what's the next one? -13, good. And then the last one is what? Okay. All right, any questions on this? So we've transformed, we started with A on the left, and then we went down and we transformed it to the identity on the left, and then we have the inverse now. And so the answer is A inverse is equal to -28 -13, 3, 2, 1, 0, -7, 3, 1. Okay.
I think it's -24 instead of -28.
I don't think so, is it? Because you have -4 times 2, that's -8 plus -20.
Okay, never mind.
Okay, all right, I think it's -20. All right, any other questions? Okay, so you can imagine doing this for like 4 by 4 or 5 by 5 or 10 by 10. As long as you have enough time and you have a large enough piece of paper. So, Okay, and the thing is, you can also check that, so you see, if you want to do this, you should check that, if you want to check the answers right, just make sure that when you take the product of those two, that's the identity. And when you take the product the other way, it's also the identity. Okay, I'll leave that for you as an exercise. All right, now what I want to do is I want to recall this equivalence, this theorem with equivalences. So this is from last time. So the following are equivalent. Okay. So here A is an n by n matrix. And so here's the first statement. A is invertible. Okay. So that's the same as saying that A has n pivots. Okay. So if it doesn't have n pivots, we wouldn't be able to do this process, right? So in some ways, you can kind of see why it's true. If you have n pivots, then AX equals 0 has only the trivial solution. Four. So we saw that if you have something having just the trivial solution, then the map has to be 1-to-1. Okay. Now, if it's 1-to-1, the columns of A are linearly independent. All right. Now, also, if you have n pivots, then if you look at the general solution, AX equals B, then it has a unique solution. So AX equals B has a unique solution. Okay. 7, if it has a unique solution, then the columns, if it has a solution, the columns of A span Rn. So we saw that having a solution actually says that B is actually in the span of the columns of A. And then if this is true, then A from Rn to Rn is onto. Okay, so this encapsulates the idea of invertibility, the ideas of Gaussian elimination, the ideas of homogeneous systems of equations, general systems of equations, linear independence, spanning, and 1-to-1 and onto. Okay, so this theorem is like everything under the kitchen sink. Any questions on this?
Yeah, I have a question.
Sure.
So does this mean for any n by n matrix, if it's onto, it's also 1-by-1?
Yes.
And vice versa. Okay.
Exactly. That's right. That's exactly what it means. Okay, so those are equivalent statements for n by n matrices. Okay, other questions?
Yeah, so if one of these statements is false, and are they all false?
Yes,
Okay, so that's all true or all false. Okay.
that's right, because they're equivalent statements. So if A is invertible, that happens if and only if A is onto.
Okay.
So if A is not invertible, then A is not onto. Okay, and vice versa. So they're all saying the same thing. That's right. All right, now let's see if we can just apply this to solve the following example. Okay, so the problem is determine if A equals 1, 4, 2, 2, 7, 3, 1, 7, 5 as an inverse. Okay, so I want to know whether this matrix is invertible or not. All right, now you kind of look over the list. Now I could actually try to find an inverse for it, but is there an easy way to check whether it has an inverse?
Can't we just do Gaussian, and then if it has a pivot in each spot, then it has only a trivial solution, thus it'll be invertible?
Very good. So we can do it that way. So you can also, so this is basically the same. So why don't we just look at the homogeneous system and see whether it has just the trivial solution or not. Okay, essentially you're going to see this anyway in terms of pivots. Okay, so we're just going to do exactly what you're saying, 1, 7, 5. Okay, so we're just looking at AX equals 0. Right? And we want to see if there's a free variable or not. Okay, so let's do this. So, you just apply Gaussian elimination. So 1, 4, 2, 0, 0. What do we get? We get -1, right? And -1 here, and a 0. Okay, and then I'm just going to apply. Let's see. I'm going to apply -1 to row 1 and add it to row 3. 0, 3, 3, 0. Okay. So we just continue on. 1, 4, 2, 0. Multiply the second row by 3, add it to the third row. So we keep the second row the same. 0, 0, 0, 0. Okay, conclusion?
It's not invertible.
Not invertible. Okay, so there are 3 variables. So namely, x3 equals t. So there are infinitely many solutions. To AX equals 0. So it doesn't have just the trivial solution. So hence, A is not invertible. Good. Does everyone see the logic behind this? So you can actually use various methods to check whether a matrix is invertible or not. And one of the methods you can use is Gaussian elimination. Okay, good. Yes. Well, if you had any pivots, you'd be okay. So then, yeah, so one of them is true, all the others are true. Okay, so that's what it means by the following statements are equivalent. Okay, so statement, let's say D means the same thing as statement A. Okay, so that's why it's nice, because once you have equivalent statements, sometimes you're in various contexts, and one statement's easier to apply than something else. And so in this case, it's easy to apply Gaussian elimination. Okay, good. All right, now let me just mention a little bit about what inverses are in terms of linear transformations. So let T from Rn to Rn be a linear transformation. Okay, so So here we're assuming we're going from Rn to Rn, okay, the same vector space. So then T of x is going to be equal to A times x, where A is T of E1, put that down the column, T of E2, put that down the column, T of En, and put that down the column. Okay, so we've actually represented using matrices. Okay. Now suppose A is convertible. Okay. And so what we can do is we can consider A inverse as a linear transformation from Rn to Rn. Again, okay, it's just a matrix, it's still an n by n matrix. And so I can define S of x be equal to A inverse times x. Okay, so again, S is a linear transformation from Rn to Rn. And so let's compose T and S. So take the composition of T with S, and let's say S with T. Okay, so these are functions, so you can actually compose them. All right, so let's look at T composed with S. Apply to X. This is T of S of X. This is T, okay, so I'm going to put in the matrix A inverse times X. Okay. Now I'm going to apply the definition of T. So that's A times A inverse on X. And this is the same as A times A inverse times X. And lo and behold, it's X. All right. And now what I'm going to do is I'm going to do it the other way around. So S of T of X. This is what S of A of X, which is A inverse A of X. And the answer is the same, just X. All right. So I have T composed with S is the identity, and S composed with T is the identity. So what is the conclusion about S?
S is the inverse of T.
That's right. S is the inverse of T. So the linear T is invertible, and S is equal to T inverse. Okay. So I mean, you've seen this before. For example, if you take f of x to be equal to x cubed, then the inverse function is x to the 1/3, right? Okay. So I mean, you've seen inverse functions before in calculus. So this is an example of where you have an inverse function. All right, so let me just write a summary on this. So summary. So T from Rn to Rn is invertible if and only if A is invertible. Okay, so here T of x is equal to A times x. Okay, moreover, the inverse function is equal to A inverse times x. Okay, so if you have invertibility, you can write the inverse in terms of the inverse of the matrix. Okay, any questions on this? Okay, good. All right, so I'd like to finish off with some questions. I have 3 questions. And I'd like to use our knowledge to answer these questions. Okay. So question 1. So explain why a squared is invertible if a is invertible. Okay, so assume that I have an invertible matrix, a square matrix. I want you to explain why a squared is invertible. Okay, so I'll just throw this out. So anyone have any sort of ideas?
If you separate a squared into just a times a, and then you also, when you multiply it to the inverse squared, which would be a inverse times a inverse, either way you'd equal the identity.
All right, good. So the idea is we actually kind of know what the inverse should be, right? So why don't we just consider C, which is A inverse times A inverse. So this exists because A is invertible. Okay. All right, so now I can just multiply C times A squared. So A squared times C, that's A squared times A inverse times A inverse. And as you know, this is just A times A times A inverse times A inverse. Okay, now I can just group it whatever way I want. So this is going to be A times identity times A inverse. And that's A times A inverse. And that's identity. Okay, so A squared times C is the identity. And then you could just do the same thing. So C times A squared. So let me do similarly. This is also good identity too. All right. So I have a matrix such that the product times A squared is the identity on both sides. So that means that A squared is invertible. Okay, any questions on this?
This would hold true for every even power of a, correct?
Actually, it holds true for every power.
Every power?
Yeah, that's right. So good observation. So, so more generally, I'll write your comment down. If let's just say the power is positive, okay, so n is bigger than 0, positive. So if A is invertible, then A to the n is invertible too. Okay, so like A to the 100th is invertible also. A to the 101st power is also invertible. And you just use the same argument. You just kind of can construct the inverse by taking, the inverse of A and then multiplying it out n times. Okay, part 2. All right. So show if A has linearly independent columns, then A has linearly independent rows. Okay, so here A is always n by n. Okay, so it's not true if A is not n by n. If it's a square matrix, this is true. All right, so let's try to reason this out. So suppose A has linearly independent columns. So what do we know about A?
It has n pivots.
Okay, it has n pivots. It's also invertible, right? Now, what we want to show is that the rows of A are linearly independent. But the rows of A are the columns of what?
A transpose.
A transpose. So we want to kind of get from A to A transpose. So remember we had that formula which said the following, that A transpose inverse is equal to A inverse transpose. So what that says is that if A is invertible, then A transpose is invertible too. Okay. All right, now if A transpose is invertible, then it has to have linearly independent columns. Yes. And as you said, A has linearly independent rows. Okay, so we're using a bunch of different concepts. We're using that equivalence that theorem involving all those equivalences. And so we're able to use that with some logic to actually argue this point. Okay, questions? Okay, so I have one more. I ended a little early today. Okay, so the last question. Show if A times B is invertible, then A is invertible. Okay. All right. So we have invertibility for A times B. We want to show invertibility for A. So we can pick one of these equivalent statements up here and sort of argue using one of these equivalent statements. All right. So which one do you think we should kind of think about using? So if we know B is invertible, what do we know about the homogeneous system?
It has a unique solution.
Right. Okay, so why don't we sort of argue it this way? So why don't we just look at the homogeneous system and try to show that, oh, I think I made a mistake. I apologize. Okay, so A, B, so this should be B as invertible. Okay. That's probably better. Okay, so to show the invertibility of B, we're going to show that the homogeneous system has only the trivial solution. Okay, so consider the homogeneous system Bx equals 0. Okay? All right. So the goal is to show that x is equal to 0. All right? So what should we do to this? to show x equals 0?
B inverse.
Well, we don't know whether B is invertible yet. Is there something else we can use? What's our hypothesis?
AB
Is what?
invertible, then B is invertible.
No, the hypothesis is just that A times B is invertible. Right? The conclusion we want to make is that B is invertible. Okay? So now we know A times B is invertible. So what do you think we should do?
Show the homogeneous system A, B, x equals 0 has only the trivial solution.
Yeah, so what should we do to this equation?
Multiply both sides by A.
Right. Okay, so now multiply both sides by A. Okay, so I have A times bx equals A times 0, which is 0. So I have AB times x is equal to 0. Okay. All right. Now we have A times bx is equal to 0. We know A is invertible. So what can we conclude?
That AB have, like, it's only a trivial solution, thus B is invertible.
Yes. So since AB is invertible, it follows that we only have the trivial solution, so x has to be 0. Okay? So what have we shown? We've shown that if b times x equals 0, then x has to be 0. So let me just say this. So therefore, bx equals 0 has only the trivial solution, x equals 0, thus b is invertible. Okay? So again, let me just highlight this. So I don't know if I want to call it a proof or not, but let me just kind of indicate just to make it clear. So we look at the statement. This is the hypothesis. Okay, so that's what's given to you. Okay, so you can assume that A times B is invertible. And then this green part here is what you want to conclude. Okay? Now you can't assume the conclusion. You see this a lot on TV. When people want to argue their point, right, in terms of politics, and then they assume the conclusion. But you can't, you're not supposed to do that. So you can only assume the hypothesis. And then from the hypothesis, you have to sort of logically reason down to the conclusion. Okay, is that clear how we did this? Okay, good. All right, so let me, I'll stop here. Do people have general questions about the material? People here? People online? Okay, so I will stop here a little bit early today, and so we'll see you on Friday.
Thank you.
Welcome.
You-
Okay, see ya.
So Monday's lecture is going to be, or you said it's going to be recorded, right?
Yeah, the bottom of the report.